Alright, welcome back to another Linear Algebra Final Review video. This is going to be the last video, the part 3 video, where we talk about eigenstuff. Now, if you haven't been watching through this series, in the part 1 video we talked about linear transformations, we talked about matrix algebra, matrix multiplication, inverse of a matrix stuff, and we talked about determinants and the different methods that we use to find those. Now in the part 2 video, we talked about vector spaces and subspaces, we talked about the null space, the column space, the row space, we talked about change of coordinates, we talked about dimension and rank, and we also talked about change of basis, okay? So, before we get into more of the specifics about what we're going to be talking about in this video, I really wanted to make sure that you are subscribed to this channel because I'm going to be putting out much more math content and of course physics content as well. So, if you're in linear algebra now, you might be taking ordinary differential equations next semester, and I will have a final review posted for that, as well as an overview for that course, and I'll do overviews for other courses too, such as partial differential equations and so on and so forth. Okay, so you definitely want to go check those out. And now that I've said that, let's hop into this video. So in the part 3 video, this will hopefully go a lot quicker because we have 8 problems rather than 12 or 13 as we had in the part 1 and part 2 videos respectively. And we just have 3 topics in this video. And I couldn't do the whole rainbow array of colors that I usually do, the really nice organized. So I tried to do RGB, but then it would look too Christmassy with red and green right next to each other. So I just chose to do like a blue in the middle. Anyways, on to things that really matter. We have eigenvalues and eigenvectors first, and then we have diagonalization. So we'll talk about the diagonalization of a matrix, what that's good for, things like that. And then we'll have a question on eigenvectors and linear transformations, just to, as like the putting the nail in the coffin, just making sure that you are set for your linear algebra final. Okay, all that being said, let's move on to our first problem, and that's going to be problem 26, because as I mentioned in part 1 we did 12 problems, and in part 2 we did 13. Okay, so we are now on problem 26, and for this problem we're going to have that just regular matrix equation ax equals b, and we have that A is a 2 by 2 matrix, and we are trying to find if this vector 1, 1 is a eigenvector of A. If so, then what is the corresponding eigenvalue? Okay, so what is a eigenvalue? What's an eigenvector? What does that even mean? Okay, that's probably the first thing that we should talk about, because maybe you don't have as good of an intuition for it. And actually, not just to give quick props to 3 blue 1 brown. That's actually how I ended up learning this whole eigen stuff. And I was really confused in the course itself in linear algebra, so I actually took a look at his video he explained it graphically what an eigenvector was, and it actually really gave me a good intuition of all this stuff. But a quick TLDR of what those things are. An eigenvector is basically a vector where when you do a linear transformation of it, it does not change direction. It may change length, but it won't change direction. So if we have a transformation from R2 to R2, okay, so we're going from R2 to R2, maybe we have a vector pointing in the y direction, okay? We have a vector pointing in the y direction, and we'll call this A, okay? But when we transform this vector, okay, we will still get a scaled version of that same vector, but now pointed in it's still pointed in the same direction, okay? So a vector that does this is called a eigenvector. Okay? I don't know why I'm writing with orange here because I'm on a red section, but okay. Perfect. So anyways, the amount that this vector is scaled by, okay, the amount that this vector is scaled by, so whatever the factor is from here to here, is called the eigenvalue. Okay? And if the vector doesn't change length, then its eigenvalue will be 1, right? The eigenvalue will be 1 for that corresponding eigenvector. Okay? So how do we see if we get 1, 1 to be an eigenvector? Well, what we actually have to do here is well, multiply that transformation, the standard matrix A, right? Our transformation matrix. We're multiplying it by x, right? We're going to do the transformation to x and see if it is going to be a scalar multiple or just the exact vector kind of is included in that group. Okay? So we have A times x. Okay? So let's do that. We get 1 times 1, 0 plus 1 times 1, 2. And so we end up getting a 2, 2. Okay? Now we can see here that this vector is a scalar multiple of this vector. So the answer is yes. 1, 1 is an eigenvector of A. Okay? The corresponding eigenvalue, what would that be? Well, we don't even really need to dive too deep into the whole equation business, right, with the like the A minus lambda I and all that stuff. We don't need to dive too deeply into that yet. Okay? Because really the only equation that you need to think of here is that AX equals lambda times x. Right? So you apply the linear transformation to x, and it's the same thing as if you scaled x. Right? That's the idea. That's exactly what I said earlier. Right? So this lambda here would end up being 2 because we transformed it from 1, 1 to 2, 2. We scaled it by 2. So, and by the way, lambda is the symbol for the eigenvalue, so the corresponding eigenvalue is 2. All right, and that does it for our first problem. So now we're going to move on to problem 27, which is asking us to find all eigenvalues and eigenvectors of our 2 by 2 matrix A, which is 2, 1, negative 6, negative 3. Okay, so now we're actually going to have to go through and start off with that AX equals lambda x and figure out how we actually find our eigenvalues, and then we're going to find our eigenvectors off of those eigenvalues. Okay, and the reason why I'm saying we're going to go through all that is not because I want to bore you or just be like, oh, okay, I don't need to know this because all I need to know how to do is the problem. And that may be true for some of you, right? But then you don't fully understand it. Okay, and the reason why that's bad is because then it becomes easier to forget. Okay, and you already have enough things to memorize for this test, so I feel like the least I can do is show you how you actually go about finding eigenvalues from the start, from the AX equals lambda x equation. So starting off with that AX equals lambda x equation, first off, remember what this is saying. As I said in the last problem, we're saying that if we transform a vector x, okay, that it's the same thing as scaling that vector x, okay, whether by 1 or 2 or whatever. The important part is that the vector maintains the same direction. Okay, if we subtract lambda x on both sides, we get ax minus lambda x equals 0. Okay, and now we can factor out ax. Okay, but that doesn't really make sense because this is a matrix and this is just a constant, right? Lambda is a constant. So what we do is we can multiply it by 1, aka the identity matrix. Okay? And that will make these two things compatible. Okay? So now what do we do with this thing? Well, basically this kind of all comes back from the invertible matrix theorem. Okay? Because we want to find the eigenvalues first. So we want to find all values, all values of lambda, okay, so that we make that standard matrix, we make that new standard matrix, A minus lambda I, we want to make it linearly dependent. Okay? So, why would we want to make it linearly dependent? Well, as I said, that stems from the invertible matrix theorem. If it's linearly dependent, then there is a non-trivial solution. Okay? There's a non-trivial solution for this equation. Right? Meaning that it's not just, okay, well, if you break off x into x1 and x2, it's not just that these two things are 0. You're going to get an actual eigenvector from this, okay, if this thing is linearly dependent. Okay, so that's why we go and do this. So let's actually, and by the way, if it's linearly dependent, then it is not invertible, right? So if it's linearly dependent, it's not invertible, and if it's not invertible, it has a determinant that's equal to 0, and that's why we take the determinant of this, okay? So let's go through and actually do that. So what this essentially does is it subtracts lambdas across the diagonal. So we'll have a 2 minus lambda, and you can, check me on that and all that, but for the sake of time, I'll write it like this, okay? And we want to see where the determinant of this equals 0 for reasons I just mentioned. Well, if we find the determinant, that's the same thing as 2 minus lambda. We have a negative 3 minus lambda, and then we have that's minus a 1 times negative 6, and we set that equal to 0. And we end up with this will be a negative 6. We'll have a plus lambda squared, and we'll have a plus lambda. Okay, because we have a minus 3 minus lambda gives us plus 3 lambda, and we have a minus 2 lambda because of these two things. Okay, and then we add 6 and get 0, so we have lambda squared plus lambda equals 0. So we get that lambda equals 0 and lambda will equal negative 1. Okay, and just because I skipped a step there and I feel bad about it now, I can write it like that. Okay, in which case you see where I'm coming from now. Okay, so these right here are our eigenvalues, right? But we have to find the eigenvectors that correspond to these eigenvalues, right? So when lambda equals 0, what we're going to do is we're plugging it into this new standard matrix, A minus lambda I. Okay, so we have 2 minus lambda, okay, we have 1, negative 6, and negative 3 minus lambda, and we plug in 0. Okay, and we're going to augment this with zeros. Okay, so that's going to help us find the eigenvectors, and we get a 2, 1, negative 6, negative 3 when we plug in 0 for lambda. We augment this with zeros, and you'll see that the bottom two, right, these two, this second row is a scalar multiple of this row, right? You multiply by negative 3. Okay, and so we get a 2, 1, 0. We can zero out the second row and just get a 0, 0, 0. Right? So I can scale the first row now to 1, 1/2, 0, 0, 0, 0. And, well, there you go. So what you can do is write this eigenvector, okay, as, well, you have x1 here equals a negative 1/2 x squared, or sorry, x2. And so this eigenvector can be written as negative 1/2, 1, right? Because x2 is a free variable, and x1 is going to be negative 1/2 x2, right? So this is kind of the same thing as x2, negative 1/2, 1. But we get rid of the x2 because we're just talking about this thing. This is our eigenvector for lambda equals 0. For lambda equals negative 1, we can repeat this. Okay, if we go through and put that negative 1 in, we'll have a 3, 1, negative 6, and then negative 3 minus a negative 1 is going to give us negative 2. Okay, and again, we augment that with 0. Okay, so we get again that the second row is a scalar multiple of the first row. We just multiply by negative 2 this time. And so we get 3, 1, 0, 0, 0, 0. And so we get 1, 1/3, 0, 0, 0, 0. And so now that vector is instead negative 1/3, 1. Okay, that is the E vector for lambda equals -1. Okay? And that is basically how you find the eigenvalues and eigenvectors. It's actually not that terrible of a process, but it's just understanding where all that's coming from. That's the hardest part, because if you know that, then you'll understand how to go through and do this. All right, so moving on to problem 28. We are asked to let AX equal B, where A is a 3 by 3 matrix, and we want to find three things. We want to find the eigenvectors corresponding to the eigenvalue lambda equals 2. We want to find a basis for the corresponding eigenspace. Okay, this is not the same thing as an eigenbasis, by the way. And we want to see what happens to the vectors in the eigenspace during the linear transformation. Okay, so the last question is kind of just subjective, okay? But for the first problem, okay, that should be probably the simplest thing, right? We want to find the eigenvectors corresponding to the eigenvalue lambda equals 2, okay? So what do? Well, let's rewrite this matrix A, okay? And, well, if we want to find the eigenvectors corresponding to this eigenvalue, what we're going to do is just subtract lambdas down the diagonal, right? Okay, and here's why we're doing that, by the way. When we just to recap, right? We have a minus lambda I. Okay, so you have your standard matrix minus, basically you have lambdas down the diagonal. Okay, right? That's what lambda I actually is. This is lambda I. Okay, so that's why you get minus lambdas down the diagonal. Okay, I feel like I should finally say that. So now what do we want to do with this matrix? Well, we have that lambda equals 2, so let's plug that in. We get a 2, 2, 2, -1, -1, -1, and a 6, 6, 6. So basically we just have a 2, -1, 6, and then we have zeros all underneath because we can zero out those rows now. Okay, what do we do with this? Well, remember, we need to augment this with 0. Okay, and something else I didn't mention earlier, why we augment with 0. Remember, we have we have a minus lambda I x equals 0, right? So we're augmenting with this 0 vector right here. Okay, that's why. So this 0 vector is right here. Okay, and your a minus lambda I is right here. Okay, that's this thing. So we're doing this to find our eigenvectors, which is x. Okay, so sorry, I should have said that earlier. So now we can just scale down. We get a -1/2 here. We get a 3 here. Okay, and now we get that our x is equal to, well, remember, this is going to be x1, x2, x3. We're dealing with something in R3 here. So we can write x1 as a 1/2 x2 minus 3 x3. Sorry, this is not x squared, it's x2. And then we'll have a x2 and x3 because both of those things are free. So now we can split this up into two respective vectors, right? Eigenvectors. We have 1/2, 1, 0, and we have -3, 0, 1. These are our eigenvectors. Okay, so our eigenvectors are 1/2, 1, 0, and -3, 0, 1. So we have two eigenvectors for this one eigenvalue. Okay, so these are our eigenvectors. Okay, and that was what number 1 was asking, but number 2 is asking to find a basis for the corresponding eigenspace. So what is a eigenspace? Okay, well, basically it's the span of those eigenvectors. Okay, so if it's the span of for a given eigenvalue. Okay, a given eigenvalue will have its own eigenvectors, and well, it could be eigenvector or it could be plural eigenvectors, and then it will have an eigenspace. Okay, and basically, let's say we have one eigenvector. Okay, if we have one eigenvector, then the eigenspace is basically the span of that vector. So it would be a line, right? It'd be a line. So any vector on that line, when you have that linear transformation occur, everything on that line will get scaled by that eigenvalue, but it will not change direction. Okay? So that is the idea, but now we're doing this with two vectors. So now we have vectors possibly on a plane, but we have to check, right? For step 2, our eigenspan, or not eigenspan, sorry, eigenspace, is going to be the span of 1/2, 1, 0, and -3, 0, 1. This is definitely our eigenspace. But now we need a basis for it. So we need to prove that these things are linearly independent. So we put them in a matrix. And well, what we can do now is just scale up the first row. We can actually zero off this -6 right here relatively easy without any pushback here, because this is a 0 value here. So we can use this 1 to zero it off. Okay, so we can have 1, 1, 0, 0, 0, 1, in which case the second row is now a copy of the third row, or sorry, of the first row. So we get 1, 0. We'll bring the third row up, so we get 0, 1, and then we bring the zeroed out second row down to get 0, 0. So these things are linearly independent, and so this is also a basis for the eigenspace. Okay, so we can write that these things are a basis for the eigenspace. Now we move on to part 3. Okay, so that's to remind you what happens to the vectors in the eigenspace during the transformation. Okay, so we have these linear combinations of eigenvectors. Okay, it's two-dimensional, so that means that we're dealing with a plane. Okay, we're in R3, so we have this plane in R3. Okay, and any vector that's on this plane before the transformation will be on the plane after the transformation, but it will be scaled by a factor of 2, right? Because our eigenvalue is 2, right? So that's going to be true for any vector on the eigenspace, okay, on the plane. Okay, so that's the answer to number 3. Okay, to put that on paper, the vectors in the eigenspace will be scaled by a factor of 2, but will not change direction during the transformation, during the linear transformation. Right, and that is your answer to number 3. So now we've answered number 1, 2, and 3. We first found the eigenvectors for lambda equals 2. We found the eigenspace, and we found a basis for the eigenspace. Okay. We then found, lastly, the vectors. We found what happens to the vectors in the eigenspace during the linear transformation. So moving on to problem number 29. We're now going to shift our focus to diagonalization, okay? And we're trying to see if this 4x4 matrix is diagonalizable. That's a really hard word to say. Diagonalizable. Diagonalizable. Okay, whatever. Anyways, so what does it mean? What is diagonalization even talking about? Okay, because when I got into this topic, I was like, okay, what's the purpose here? And really, there's not much, I guess. It's just kind of like taking matrices to exponents. It's really easy when you are able to diagonalize them. Okay, so basically it comes from, if this is called matrix A and we want to take like A cubed or something like that, right? Well, we describe A, we set A equal to P D P inverse, right? Yeah. So when we want to cube A, what happens is, well, actually, let's just talk about squaring A for now, because it'll make it a little simpler to write. We get PD P inverse times PD P inverse. Okay? And what happens is P inverse times P is the identity matrix. And so what happens is you get A squared equals P times D, which is D squared, P inverse. So it's a nice easy way, and a diagonal matrix is much easier to square. Okay, because what a diagonal matrix is you have all other values are 0 except for the values on the diagonal. So it's like 3 and 3, right? So you'd square these two values, and that would equal D squared. So you'd get 9009. You then multiply it by P, right? This being the second matrix in that matrix multiplication. Remember, order matters. And then you multiply it by P inverse. Okay? And that is the way in which you can actually find A squared. Okay? So, and of course, A squared, why don't you just multiply the matrices together? Well, yeah, you can make that argument, but what if you have like A to the 98th, okay, or A to the 100th? It becomes a lot easier, or a lot harder, but it will be easier to use this method by far. So that's where the whole diagonalization thing comes in. You don't really see too many applications of it, or if any, in linear algebra. You just get to figure, to know it, right? So I thought that was kind of silly, but anyways. So how do we know if we're able to get a matrix D from A? Well, basically the theorem behind this is that A is diagonalizable if A has n linearly independent eigenvectors. Okay? Now, in our case, we have our eigenvalues sticking right out here on the diagonal, right? So we have an upper triangular matrix, and what that means is that our eigenvalues are right on the diagonal, okay? So since we have that, well, we know that we have to have linearly independent eigenvectors, okay? So you can say that this matrix is diagonalizable because your eigenvalues are distinct. Okay. Now, as a quick note, if that didn't kind of resonate too much with you, don't worry, because we're going to be doing another problem on diagonalization right now. So moving on to question 30, we are being asked to diagonalize the matrix A, which is a 3x3 matrix, and we want to find the eigenbasis. Now, when you have diagonalization problems, you generally are asked to find the eigenbasis because the eigenbasis is P. Right? The eigenbasis is P, so you have P, D, P inverse, right? So you have P, which is your eigenbasis, and D, which is your diagonalization, okay? So that's why you always see eigenbasis, right? So this thing is P. So this diagonalizing a matrix is a multi-step process, okay? And in that process, you do end up finding the eigenbasis, okay? For step 1, right, this is a 4-step process, we have to find, and I shouldn't have gone away from that color so soon because I want to write the step in it. So we want to find the eigenvalues of A. Now, this may require some grunt work if you're not given a matrix as nice as the one I gave you, but here you can see that lambda equals 1, 2, and 3, right? Those are our eigenvalues going right down the diagonal. We know that because this matrix is upper triangular, so the eigenvalues are right down the diagonal. The next thing that we want to do, okay, is we want to find, and this is probably the lengthiest step, we want to find n linearly independent eigenvectors of A. Okay, so now we need to actually go through and find the eigenvectors. So what we do, remember we augment this with 0. I showed you y already. Okay, and instead of having it be this though, you have to subtract lambda down the diagonal, right? So our first lambda is 1. So, and actually it's kind of incorrect to augment this with 0 yet because this is just A. But what happens is I'm going to subtract 1 down the diagonal and then I'm going to augment with 0. So we get 0, 4, 6, 0, 1, 5, 0, 0, 2. Right? And now we augment. So we can simplify this to be 0, 2, 3. We're going to actually, I'm going to do a, well, not yet. Let's do this for now. Yeah, let's do it just like that. And then we'll have a 1 here. And then again, you need to remember to separate this thing and augment it. Keep forgetting in this video. Yeah. So what I'm going to do here now is I am going to just scale down this first row and get 0, 1, and this 3 would have to become a 3 halves, but that's unimportant. Okay, we don't have to deal with anything gross here, because what I'm going to do is I'm going to perform a row swap between rows 2 and 3. Here's actually why, and this is just making row reduction as easy as possible for yourself. I can actually go right from this step and write this thing as 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, but how am I able to do that? And if you've been watching in these, you know, these the part 1, the part 2 video, you've seen that I've done this a lot. Okay, since this value is 0, when I perform row reduction, it won't change this value, but I can zero out this value, the 3 halves. Right? So I can make that 0 and not have to worry about anything. The same goes for the third row. I can make that all 0 because this 1, okay, well, this is now going to be 0, by the way. So this 1 will be able to zero out that 1 without any effect on this 5, right? And even if there was, it wouldn't matter. Okay, so I guess it really doesn't matter what order it is, because this 1 will be able to zero out this 5. And the reason for why that wouldn't affect anything else is because there's zeros in the rest of the row. Okay, so that's why I'm able to write it like this. Okay, now here we have that x1 is free if we label these x1, x2, and x3. And you know what? I'm going to say something real quick. I hate how we have to label them as x1, x2, x3. Like, I could label them as x, y, z, but I've grown so used to them being like x1, x2, x3, and I hate it. Like, I just want them to be like x, y, z, and if you have to out of like a 4th and 5th dimension, you have a and b. Because I swear to God, I hated that when I came to linear algebra. Okay, rant over. So we get that the vector x here is, well, x1 is free, and so this is just going to be x1, and then x2 and x3 are 0. So we are just getting 1, 0, 0 as our eigenvector here. Okay, that was only the first one though, so now we actually have to do that 2 more times. And so if we subtract 2 down the diagonal of A, we get a negative 1, 4, 6, a 0, 0, 5, and a 0, 0, 3. Sorry, 0, 0, 1 now. So we can zero out the third row. We can't scale down the second row, or you could just perform a row swap and zero out the now third row. Doesn't matter. You guys see what's going to happen here. Okay, we get that. We can augment with zeros, of course. And we can zero out this 6 here. And we can also, we'll get this thing to be a 1, so we will scale by negative 1. So we'll have a 1, negative 4, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay, and here you see that x is equal to, we have x2 is now our free variable. So x1 is actually going to be 4x2 when we have x2, and x3 is just going to be 0. Okay, so we get a 4, 1, 0 as our second vector. And now when we subtract by 3 across the diagonal, and I can just look at this and then subtract an extra 1 down the diagonal, we'll get negative 2, 4, 6, 0, negative 1, 5, and a 0, 0, 0. Okay, here we can scale down the first row by negative 1/2. Okay, so we'll get a 1, 2, negative 2, negative 3, and we'll have a 0. We'll scale this by negative 1 as well, so we'll have a 1, negative 5. Okay, and now all we're going to do is zero out this negative 2 here. And of course, again, forgetting to augment with zeros. What's going on with me today? And this is also the same day that I'm making the part 2 video, so whatever. So we get 0 under the first pivot. We have a 0 under the second pivot. This thing goes to 0. To get that to 0, I have to multiply the second, or the first row, the second row by 2 and then add. So if I multiply the second row by 2, I'll get a negative 10, and add that to negative 3, and I'll get a negative 13 here. And then I still have a negative 5 here. And I'll have a 0, and that'll be 0, like so. Okay, so I'll get that x is equal to, and now we have x1 and x2 being described in terms of x3. So x1 is 13 x3, x2 is going to be 5 x3, and then x3 is free. So we get 13, 5, 1. Okay? So now we have our linearly independent eigenvectors. Okay? And we have n of them, right? We have n, which is 3 here, right? We have a m by n matrix, that being a 3 by 3 matrix, so n is 3. Okay? So we move on to the third step. Okay, now that we found these things. And step 3, okay, is to construct P. Okay? From the vectors in step 2. So construct P by forming an eigenbasis. Okay, so the eigenbasis is just going to be the vectors that you had. So we have 1, 0, 0, we have 4, 1, 0, and we have 13, 5, 1. And those all go in a matrix, and there you go, that's P. So now we have P, and we move on to step 4, which is to construct D. And we construct D from the corresponding eigenvalues. Okay, so this was our lambda equals 1, lambda equals 2, lambda equals 3 eigenvectors. And so we're going to have 1, 0, 0, 0, 2, 0, 0, 0, 3. And that, my friends, is D. Okay? So there you go. We diagonalized the matrix and we also found our eigenbasis, which is P. Okay? And you can even make a little arrow to that saying eigenbasis. Okay? So I think I falsely mentioned that in the beginning of this video that there was going to be 8 problems. There's actually going to be 6, I believe. Yeah, 26, 27, 28, 29, 30, 31. Yeah, 6. So you get a break, I guess, right? So our last problem, problem 31, is on eigenvectors and linear transformations. So it's kind of like change of basis, but now for linear transformations. And actually, I think most students find this easier than change of basis in general because it's kind of a set process for this stuff, and there's a very limited selection of problems that you would get because, I think for most linear algebra classes, this is like at the end of the semester and it's barely squeezed in. So you really don't have any problems like this on your final. If you do, it's like one problem and it's fairly straightforward. Okay. But of course that could be different for some of you. And so I don't want to over simplify how linear algebra classes are run in all across the world. So let's get into this problem. So we have a transformation from P2 to P2, okay? And we have the transformation takes some polynomial P, and it becomes that polynomial subtracted by its derivative. They like to throw in derivatives a lot with these problems, so I definitely wanted to make sure I included that. Okay, and we want to find that transformation relative to another basis, B, right? And right now it's relative to a standard basis, okay? So now we're going to put it relative to the basis B, 1x, x squared. Okay? So now this is like a 3-step process, right? So what we end up doing is, first off, we're going to find what our basis is, right? If you transform 1, right? What do you get? We're going to transform the different components of the basis. Okay? And we get that. So actually, I'll write that down so I'm not too disorganized here. 1, transform components of basis. Okay? So if we transform 1, we will get, 1 minus its derivative is 0, so we get 1. If we transform x, we will get x minus its derivative, which is 1, so we get, that's x minus 1. And if we transform x squared, we will get x squared minus its derivative, which is 2x, right? So, and by the way, if you're confused on where I'm getting that from, it's right here, p minus p prime. Okay, and that's coming from, we're starting from p, right? So p being, 1 here, and we get p minus p prime. Okay, so just make sure everybody's on the same page here. Okay, so that's the first thing. And then the second thing is we want to coordinatize. I don't know if I'm spelling this right. Okay, we want to coordinatize these transformed components. And we want to do that relative to the new basis. Right, which in this case is B. Okay, I know it's kind of an easier one to do because it's the standard basis for P2, but I mean, I don't think you would get anything too hard anyway. So okay, so T1 relative to B would be, we have a 1 here, so this would be a 1, 0, 0, right? We don't have any x's, we don't have any x squareds. For t of x relative to b. So we transform x, and we have an x minus 1. So we have the negative 1, right, from this negative 1. X has a coefficient of 1, and then we don't have any x squareds. Then we have t of x squared relative to b. And we see that's x squared minus 2x. We don't have any constant component to that, so we get a 0. We have a minus 2 here on our x term, and then we have that'll be a 1 on the x squared term. Okay? And well, the last step here, so there's actually a really quick process, because the last step here is to throw them in a matrix. Okay? Last step, and I didn't write that in green. Gosh darn it, hang on. No, it's gonna bug me to no end, so I'm gonna write it. Throw them in a matrix. It'd be great if I could just change color instantaneously, but that's not something I can do. So, anyways, the transformation relative to b, okay, will be 1, 0, 0, negative 1, 1, 0, 0, negative 2, 1. And there you go. Okay? And that right there is our last problem for a linear algebra final review. I really appreciate you guys sticking with me, and I really hope that this video was able to help you, and hopefully you go out and you get an A on that final, or at least you do a lot better than you had originally planned on doing. Okay, so hopefully this video gave you a whole new level of confidence going into this test. So anyways, like I said, subscribe if you're looking for some more content. Hopefully you are, and I shouldn't make that a question. You know what? Just go and subscribe, please. No, I'm asking. No, go subscribe. I'm telling you to do it. All right, whatever. I'm shot. It's like late at night, so I'll let you guys go here. I'm not on a phone call. What am I doing? All right, bye.